Alright guys, so we want to talk about finding the equation of a tangent line. Specifically here we have an implicitly defined equation, and we have the point 9 comma negative 1. Now, conceivably we could write this in explicit form. That is, we could solve that for y. The problem is if we solve that for y, we're going to get two explicit functions that define this one explicit equation here. That is, the graph of this is like a sideways oriented parabola. So it's something like this, something like that. Without being too specific here, that's what this graph looks like. The problem is if we try to explicitly define this, we'll break it apart into two halves, an upper half and a lower half. So at that point, we could take the derivative of the correct half, and then in fact the upper half, and evaluate it at that point. Actually, no, that would be the lower half. Probably evaluate at that point. We just have to make sure to pick the right explicit derivative to evaluate. Now, let's just use implicit differentiation. I think that'll be a little bit easier. So remember, the implicit differentiation, that means we're just going to take the derivative of both sides with respect to x. That we then solve for dy dx by collecting all of our dy dx terms, factoring, and finally dividing by whatever we need to in order to solve for dy dx. So the first step, though, is to take the derivative of both sides of this implicitly defined equation. So take the derivative of the entire left-hand side, and take the derivative of the entire right-hand side. Okay. Now, the left-hand side here, that is just a chain rule application. So the chain rule says take the derivative of the outside function. The outside function here, let's just say, is f equals x squared. The inside function g is y minus 3. So the chain rule says we take the derivative of the outside function, that results in 2x. But we evaluate 2x at our inside function, which is y minus 3. We then multiply by the derivative of our inside function. So what's the derivative of y minus 3? Well, it's just 1 dy dx. So dy dx. Now the derivative of the right-hand side is actually kind of nice because it only has x terms. There is no y's, so we don't have to worry about any dy dx business. So we could actually write this as 4 times the derivative of x minus 5 by using the constant multiple rule to factor that 4 out. Now what's the derivative of x minus 5? Well, the derivative of x minus 5 is just 1 minus 0, or 1. So we only get a 4 on the right-hand side. The left-hand side, we have 2 times y minus 3 dy dx. Now this is kind of nice because there's only one dy dx term. So there's no factoring involved here, which saves us a little bit of work. So to solve for dy dx, we simply divide both sides by this factor there. So dy dx equals 4 over 2y minus 3. Okay? Now that is our derivative, our implicit derivative. Notice it only has y's in it, which happens sometimes. Recall that explicit derivatives are always going to be in terms of x only. But implicit derivatives can be in terms of x, y, or a combination of x's and y's. So this one is just in terms of y, which is kind of nice. So what we want to do is find the slope at 9 comma negative 1 is given by dy over dx evaluated at this point. Now, we only have y's in there, so we only plug in our y value. So at y equal -1, which is 4, divided by 2 times -1 minus 3. Almost ran out of room there. Okay, so -1 minus 3 is -4. So 4 over -4 is -1. So we get -1/2. So our slope is -1/2. Okay? Now that we have a slope and we have a point, we can use the point slope form to write the equation of our line, which is what we were trying to do all along. Remember, the process of finding the equation of a tangent line is always the same general few steps. You have to first find your derivative. Here we had to find the implicit derivative. We evaluate that implicit derivative, or if in the explicit case, the explicit derivative. We evaluate the derivative at our point. We just did that. We get our slope. We then use the point slope form to write the equation of the line, and then almost always we're going to simplify that to slope intercept y equals mx+b form. So let's see here. Label your point. There is x1 and y1, and we know that point slope form says y minus y1, so -1, equals m, which is -1/2, times x minus x1, which is 9. So we get y, if we're simplifying this, y equals -1/2 x plus 9/2 minus 1. Because that turns to a positive 1, but we subtract it from both sides. Okay? So y equals -1/2 x. Let's see here. 9/2 minus 1. So the common denominator there is 2. We could change that 1 to 2 over 2. And then we could say plus 7/2. So there is the equation of the tangent line at that point, 9, -1. Now, I alluded to this earlier, and let's see if we can solve the exact same, get the exact same answer by first writing this in explicit form. Let's see how it works. We'll see if it is any easier or not. So if I just try to solve that for y, let's see. The left-hand side will turn to y squared. Let's see, minus 6y. Actually, I don't want to do that. Let's just go ahead and take the square root. Let's see how this works out for us. If we take the square root of both sides, we'll get y minus 3 equals, now if we take the square root of both sides, we have to use a plus or minus right here. So plus or minus the square root of 4 times x minus 5. And then if we solve for y, we simply add 3 to both sides, and we get y equals 3 plus or minus the square root of 4 times x minus 5. So there are two functions there, two explicit functions. The first function, well, I guess there really is no order here, but one of the functions is 3 plus the square root of 4 times x minus 5. The other is 3 minus the square root of 4 times x minus 5. Now, if you recall from your algebra class, that negative sign out in front of that radical means you're going to reflect across the x-axis. So like you'll have a vertical flip or reflection. So this is going to be the upper half of our parabola, and that's going to be the lower half. Think like this: we have a sideways oriented parabola. This will be the upper half. This will be the lower half. Now, we have to be careful regarding which function this point lies on. Okay. So we have to double check to make sure whichever one of these functions we differentiate, that we pick the correct one. So where does 9, -1 lie? Let's try this one. If we plug it in 9, we'll have 9 minus 5 is 4. 4 times 4 is 16. Square root of 16 is -4. 4. But 3 minus 4 gives us -1. So 9, -1 lives on this. If we try to see if it is here, if we plug it in 9, we would have 9 minus 5, okay, that's 4. 4 times 4 is 16. Square root of 16 is 4, but 3 plus 4 is 7. So if we plug in a positive 9 there, the result is 7. So this doesn't help us at all as far as finding the equation of the tangent line at 9, -1. We have to use this one. So here is the bottom half of the parabola explicitly defined. So if we take the derivative of that explicit function, we can then evaluate it at x equals 9, and we should get the exact same result we did here. Hopefully, as long as I didn't make any errors, that is. So let's see, y prime equals, okay, the derivative of 3 is just 0. But here we have a chain rule application. So let's factor out a negative sign. Then we could say, all right, we essentially have a radical. So we're going to take the derivative. So our outside function is x to the 1/2 power. That's the square root of x. Our inside function, we'll call it g, is 4 times x minus 5. In fact, we can just go ahead and call that 4x minus 20 if we want to. So the chain rule says take the derivative of our outside function, which is x to the 1/2 power. So the derivative of that is 1/2 times x to the -1/2 power. We reduced the power by 1. So 1/2 minus 1. And remember, we had that negative sign out front that I kind of factored out using the constant multiple rule. But the chain rule says you take the derivative of your outside function and evaluate it at your inside function, which is 4x minus 20. Remember, I just went ahead and distributed the 4 there. So that's the same thing as 4 times x minus 5. But then we multiply by the derivative of our inside function. So what's the derivative of 4x minus 20? The derivative of 20 is just 0. The derivative of 4x is 4. So times 4. So if we simplify a little bit, we get that y prime equals, okay, 4 times -1/2 is -2. And if we go ahead and write this in radical notation, we'll have -2 over the square root of 4x minus 20. Okay? So there is y prime. Now, that is the derivative, so that will give us the slope of all of the points on the bottom half of this parabola, including the point we're worried about, we're concerned with. So if we evaluate y prime at 9, we should get the slope of our tangent line at 9, -1. So y prime at x equals 9 is, well, it's -2 divided by the square root of 4 times 9 minus 20, which equals, okay, we have We have, let's see, 4 times 9. 4 times 9 is 36. 36 minus 20 is 16. The square root of 16 is 4. So we have negative 2 over 4, otherwise known as negative 1/2. So there's the slope. But notice that is the exact same slope we got using the implicit derivative. And now we're to the exact same point we were earlier. So now I would just repeat the process. I take my point, 9 comma negative 1. I label it as x1 and y1. I then say there is m, and I use point slope form. So y minus y1, which is negative 1, equals m, which is negative half, times x minus x1, which is 9. I get y plus 1 equals negative 1/2 x plus 9/2. And finally, I get y equals negative 1/2 x. Oh, if I subtract 1 from 9/2, we already saw that's 7/2. So we get the exact same answer using explicit derivatives as we do when we use implicit derivatives. The thing is, usually you can't do this. This was nice in the fact that we could solve that for y and write it we could solve it for y and write it in explicit form. Lots of times that is too cumbersome to even worry about. Lots of times, like if there had been, a couple more, x's and y's in there thrown in the mix, and some more, a little bit more complicated, it would have been too cumbersome to find the explicit definition of y. So we would be forced to use this process here. But if you want to, and you have the option, you can solve solve for y and rewrite the function in explicit terms. Just to recap, this information right here, not that. This information right here conveys the exact same thing as this information right here. It is that implicit function, that single implicit function, conveys the exact same information as these two explicit functions. So it takes two explicit functions to give the same information, the same graph as that one implicit function. That's why we use implicit functions, because we can get all kinds of more interesting graphs and write them in more concise forms. Okay, so if you decide to go this route, you just have to make sure that you pick the right half of y to take the derivative of. That is, if we had accidentally taken the derivative of this right here, then plugged in a x equal to 9, we would have gotten an incorrect slope. Okay? In fact, we would have gotten positive 1/2 instead of negative 1/2, which then we would have had a completely different answer right here. So you just have to be careful. If you are going to use explicit differentiation, you have to be very careful of when you solve for y, and if you get multiple explicit functions, you have to choose the correct one, and that all depends on what your original point is. We had to choose the explicit function, the one that we know 9 comma negative 1 is a part of. 9 comma negative 1 is not a part of this explicit function, so we have to choose this one. So, hope that's been helpful. If you have any more questions, feel free to ask. Again, I showed you two different ways to solve the exact same question. I would suggest this one's easier, so I would just go with implicit differentiation. But you could, in this instance, you could use explicit differentiation as well. So, if you have questions, feel free to ask, feel free to post more questions, and I'll always do my best to answer you guys. So, have a good day. Talk to you soon.